Okay. So let's get trucking. Before we add the stuff, I think I put a slide on here for what we're going to do. Next is teach the towns the roads that come out of them. Last time we finished building our graph, so all the roads are linked to the right towns. But what we effectively have is a if we looked at an individual town, a town doesn't necessarily know what roads go out of the town. And that seems like something that might be beneficial for us to be aware of as we go and look at ways of exploring this graph. Because at this point, what have we done? We've built effectively a map, right? If we're just creating from a couple of text files, we've said, hey, as this gets bigger and bigger and bigger, if we wanted to create the entire United States or the state of Wisconsin or something like that and list all the towns and all the roads that go between all the towns, it might be nice to pull a single town out of it and say, hey, what roads are you involved in? Something like that. That could be information that we are interested in. So now kind of going back and reminding ourselves on, one of the problems that we're interested in trying to solve with a graph data structure is this idea of you trying to come up with the shortest path between things. And there's some interesting optimization algorithm stuff that I want to mention in here. But like this little example starts off is like, hey, let's say you're leaving home on your way to work, but you decide, hey, I'm going to stop at the coffee shop. So there's only one path for you to take, because I'm not going to go to work first, then back to the coffee shop. I need to stop at the coffee shop first before I go to work. But then you start adding some additional stops. So perhaps you need to send a letter at the post office. Now you have two options for your trip. You could go to the post office first, you could go to the coffee shop first, but both of those need to happen before you get to work. So on and so forth. So, you look down this list, we just keep adding potential stops onto the list, but they could happen in any sort of order as long as your ultimate destination doesn't change. Right? You can go to the coffee shop, then the post office, then the bank. You can go to the coffee shop, then the bank, then the post office. You go to the bank, then the coffee shop, then the post office, yada, 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 yada. Right? And the idea would be is which of those is the best path? And the way we measure best is kind of in the eye of the beholder, right? Best could be shortest distance. Best could be shortest amount of time. If you're on slow roads, lots of traffic lights, you might be rolling the dice whether you're going to hit the lights, get them all on green or get them all on red, and that makes a big difference. An interesting example, I think, is on the next slide is anybody aware of, so UPS uses an interesting algorithm to optimize their delivery. Anybody know what they do for, go ahead.
So they take 5 possible destinations and see how fast, make an algorithm, see what's best possible way to do it. And then they take 5 sections of those 5 roads and then expand it.
Okay, but ultimately, what they're actually minimizing on is the number of left turns. So it's not just distance. They have to use distance. They're not going to go to, Milwaukee, then back to Chicago, only to come back up and go to Greenfield, something like that. So they need to have distance being involved, but they minimize within a zone the number of left turns. And I'm not necessarily sure why, but apparently it saves them hundreds of thousands of dollars in fuel every single year. Like a ridiculous number just by minimizing left turns, based on, I'm guessing, some research they did, and probably the ability for a vehicle like that to make left turns probably in residential neighborhoods or something like that. I don't know, just kind of an interesting thing. But this kind of comes down to, this is kind of the reason for this traveling salesman problem, why it's interesting. If we just kind of bump down here, well, it's a factorial problem, depending on the number of stops. If you only have 3 stops that you need to hit, it's 3 factorial, 3 times 2 times 1. But if you have 7 stops, it's 7 factorial. Now, notice the jump here. As a human being, our little example from the previous thing, well, we're going to this place and the next place and the next place. It doesn't seem like we're solving that hard of a problem. We're just kind of, it's like, oh, I'll hit the bank, then the coffee shop, I'll mail the letter on my way while I'm kind of drinking my coffee, get it about halfway down, whatever, then I'll go to work. It doesn't feel like we're solving a super hard problem, but you start noticing that even with a relatively small number of stops, the number of possible paths, possible solutions of which we can pick from, whichever one is the best for us, whatever we're measuring best, gets really big. 5,000 choices with just 7 stops. So that's just kind of an interesting thing. And then, we throw an 8th stop in there, gets a lot bigger very quick, to the point where we can imagine that if you are, again, in this traveling salesman situation where you have maybe your route hits 10 cities on a Wednesday. That's what you leave home, you got your 8-hour day, boom, 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 ultimately come home. In order to figure out what's the best way to do that, it's 10 factorial number of possible solutions. It's a lot. Does the Mac know how to do 10 factorial? There we go. 3.6 million possible ways you can visit those 10 towns. And that's just for your Wednesday, day of work. So it becomes kind of an interesting thing. So in order to solve this type of problem, which we would call an order NP problem, it's a time complexity and also a data storage problem. Because imagine if we don't necessarily know what's going to be the best choice. So the algorithm we're going to look at the high level, we're not going to implement it, but the high level is this algorithm called Dijkstra's algorithm. And Dijkstra's algorithm is an algorithm that's based on this idea of branch and bound. Basically, we're just going to try all the paths. And each one's going to keep track of, hey, how are we doing? And so each path is, we get to this town, how many roads go out of this town, subtract from that the road we just came in on. Don't just go back where you just came from, right? We can kind of discount that. Okay, but if there's 6 roads coming into town, you came in on one of them, you got 5 options for leaving town. So we're going to take all 5 and then somehow be able to report back or report to each other that we eventually get to our destination, because some of them are going to hit dead ends, right? Some of them you're going to get to a town where you've actually taken every single road out of that town at one point, but you've still never arrived at your destination. So now you have no viable roads to leave town on, yet you are in what's called a closed loop. If you kept following the algorithm, that's an infinite loop. You're just going to keep hitting the same crap over and over and over and over again to get you right back to that town. So that would just be a dead end. But the idea is that eventually, in that 10-town example, eventually you're going to come down to, I don't know, I'm just making up a number. Let's say there's, it would just depend on the map that we're dealing with, but let's say there was 20 viable solutions that didn't have you backtracking between the same towns. And now you're ultimately choosing between those 20 as to whatever one is best. But you still had to go through the 10 factorial possible options. And we can imagine that becoming very computationally expensive. And because we know how recursion works, every single time we say, well, I'm going to take this and this and this, but I can't do this next one until this guy comes back. All right, we can do that recursively. We can also do it in a multi-threaded asynchronous way where we say, okay, I'm not going to have this guy block because these are independent trips. So I'm going to rely on the multitasking ability of my operating system and just say, hey, I got 6 roads to try, no problem. Try all 6, just create a new thread for each of those guys and have the operating system manage it. At the end, those guys need to put their results into a file or something like that. We need to kind of manage that though, because we don't know what time, what order they're going to finish in. So we want to make sure that 2 guys don't try to write to the same file at the same time, and whoever saves last is the one that put it in there. We want to make sure at some level we've gathered the results of all of our, simultaneous trains of thought. That's a whole different problem to solve, but let's just assume it's solvable. It is. So we can do it in a way that doesn't block, but we're still using a lot of computing resources and a lot of time. And we see that as we add even one more town, it goes up exponentially. This could become a problem pretty quickly with modern computing. So Dijkstra's algorithm tries to discount possible paths as early as possible, and basically just throwing them out and saying, okay, this is probably not going to be one of our better paths, so let's just stop trying. So it's a little bit of an optimization on it. Kind of an interesting thing that's becoming a more and more of a reality now. How many of you have heard of something called quantum computing? Heard of it? What do we know about it? It's called quantum computing. Go ahead.
Each like binary digit can represent either right, 0 and 1 at the same time.
Yep. So instead of bits, so in classical computing, which is what our computer science program is classical computing. By the way, next year we're starting a quantum computing concentration. Exciting. Instead of classical computing having just bits 0 or 1, we have this idea of a qubit. A qubit, it's 0, 1, or what's called spin. It's a third state. It kind of operates off of this concept called Schrodinger's cat in physics, where you put a cat in a box with I think the original thing is you put a cat in a box with a degrading isotope that could be poisonous to the cat, let's say. Now, then you shut the box. You can't observe. You don't know what's going on. So you have no idea at any point in time whether the cat's kicked the bucket or not. So the cat's both alive and dead. You don't know at what time the radioactive material killed off the cat, or if it has, or if it ever will, whatever it is. But the cat is actually in 2 simultaneous states. It's called superposition at the same time. It's kind of fascinating thing. So we could say, oh, okay, well, fine. That's an interesting couple of check boxes we hit, but how could that be used to solve a problem like this? And we're not going to go far down this path, but just in general, these kinds of problems are like the bread and butter of quantum computing. Quantum computing attempts to predict all possible outcomes. Using, we don't really have a programming language yet for quantum programming, but there are such thing as quantum gates, kind of like assembly language type thing. And I'm working on an interpreter that effectively allows you to harness quantum gates. It probably wouldn't be fair to call it a programming language for it quite yet, but we're starting down that path, whatever it is. Just giving you an idea of one of the interesting things, because these all deal with this idea of quantum entanglement. We have 2 particles that are magically entangled, let's say, and whatever happens to the one particle instantaneously happens to the other one, regardless of how far apart they are. It's like absolutely fascinating, and we don't understand it, which makes it just terrifying. And think about data transfer instantaneously. If you have one particle in Paris, another particle in Milwaukee, and these guys are entangled somehow, and you pass this particle through one of these quantum gates. Let's say it's just a NOT gate, flips the bit. This guy will change too, instantaneously. Isn't that freaky? Yeah, it's just terrifying. But I mean, like in a cool sci-fi way, but it's like, but the thing we just don't know. We don't know why. We just observe that behavior. And there's this cool gate called an H gate, which if you feed it a bunch of particles, feed it, let's just say 0s and 1s. We could just think of it as bits. You feed it a bunch of 0s. What comes out the other side is 50% 0s, 50% 1s. So it's kind of like a random number generator where it 50% of the time flips the bit. Yeah, no big deal, right? Seems kind of reasonable, but is it random? Because if you take an H gate and a second H gate, you feed a bunch of 0s into this one, what comes out is 50% 0s, 50% 1s. Now you feed that into the other one, they switch back. They're all 0s again. They didn't randomize the second group. They just reverted. It's like spooky. And it's a black box. I just know something else. And that's where the superpositioning thing comes in. They were both a 0 and a 1 at the same time. And we observed a state that looked random to us, but it actually wasn't. So it's really cool. But we don't know how to harness it yet. But the punchline is related to what we're talking about here, is the traveling salesman problem is specifically one of the problems that we are, that quantum computing presumably will allow us to solve efficiently. You know, it's because it can handle large amounts of data in a very small footprint, relatively speaking. And there's actually an algorithm called Shor's algorithm, S-H-O-R, apostrophe S. That's an algorithm designed for a quantum solution. So the algorithm was written with the assumption that quantum computing exists before we were able to build a quantum machine. But now we can build quantum machines. They're just kind of sort of big. They're a lot smaller than like supercomputers and more powerful, but we don't have this as a quantum thing yet. But I'm pretty sure that like this whole entanglement thing is like, those are kind of hard to just come up with entangled particles. I mean, I think they have some techniques, but just kind of cool stuff right now that we're like right on that cusp of it. But I don't know. So from a computer science perspective, we're still in our classical computing state, and this isn't completely differentiating from it. But that idea of unpredictability really moves us away from the idea of us thinking about discrete solutions. Used to be 0, now it's a 1. On or off. It's one of those two states, not both. And as soon as we get both, or whatever, eardrums usually goes first, and then the rest of it goes. Okay, so, and we're not talking about the quantum stuff in here. It's just this problem is one of those problems that in classical computing is what's called an order NP problem. Very, very, very complex, and we start getting giant numbers of towns. Not even giant. We're seeing 7 is start getting a little ridiculous. It's going to become more and more difficult for us to represent. And at some point, not that deep into this, the number of paths we're going to have to check is going to be in the quintillions. And now it's like, okay, well, it's, it'll take longer for us to solve this problem for those 28 towns than it's going to be till like the sun burns out. Yeah, probably not something you're willing to wait for when you type in your address and your GPS. Say, take me to Wendy's on the south side or something. So it becomes kind of an interesting problem for us. All right. So what we decided we were going to do as our kind of our next step is say, right now our graph, just kind of reminding ourselves, we're reading in from our roads and our towns. So we have our roads text and our cities text. Make sure that the names of your cities here match up to the spelling in your roads. So this is a little janky, but solve the problem for us. So if you wanted to add more roads now, you can. If you wanted to add more cities, you can. And our code would just build a graph from that. So we'll say that's relatively handy in a offline data supported type thing. So what do we do down here in Maine? This was just our example thing. So we create our town collection. We go through and read in all the towns. This was us testing that guy. Here's my road parts. Where am I reading it from roads? Probably inside of my town collection. So here's my actual town collection. Here's my get towns, which returns a town collection. I already called that. Yep, there's my get towns. And I proved that that guy worked. All right, let me. Go back to my projects. I'm not going to save that because I think that might break what I had done previously. Because I was on a different computer last week. So I'm just going to make sure I load the project from where I was before. And I'm pretty positive I saved. So hopefully. Yeah. Calling our get roads our get times. All right. So we're in business. So get towns reads in all the towns, which returns a town collection. And then we have the idea of something called a road collection. Road collection, just like our town collection, holds our array of road objects as well as how many of those road objects we have. So ultimately, if we were coming down here and we were saying, what is our graph? Our graph is actually our road collection. Because the road collection holds on to the collection of roads that each have pointers to towns coming out of them. So if I had to say out of all these, what is this guy? That's our graph. This guy right here is just a container that holds all our town pointers. It's utilized by our road collection. That's why we needed to pass it into our road collection. To our get roads for our road collection. All right, but we decided, okay, you know what? As I'm adding a road between two towns, it would be nice to go ahead and let those two towns know that they have roads coming into them. Make some sense? Okay, so we're going to go ahead and add that ability. So that means we're going to have to teach a town itself. Oh, here we already have it. We have a collection of roads pointer. And then we have a number of roads and collections. We already kind of prepped it for this. But when we build a town right now, we're just giving it a string name. Now we can go a couple of different directions with this, just for the sake of argument, not like stretching this out. We've already done plenty with linked lists, and we can look at some built-in things like vectors or whatever. But let's just build a array that's big enough to hold a bunch of roads. We just know in our example here that there's no more than like 3 roads that are coming out of an individual town. So let's just say the maximum is 10 roads. Give each town enough memory that we can tack on some roads to that guy without any sort of major issue, just for the sake of time in our example. So for a town, we'll go into the constructor in town. And here's my collection of roads. We already have a thing called max roads. Oh, what did we choose for max roads? 10. Soothsayer. Or selective memory, I guess. So anyways, we came up with 10. We don't have the ability to add a road yet, though, so we do need to do that. So as of right now in our constructor, a town, when he first gets built, sets his town name. Initial number of roads is 0, and he has enough memory to hold, in this example, 10 roads. Okay, but now we need to give him the ability to add a road to a town. So we'll go up in here, and this guy will be a void. Call this guy add road. He'll take a road pointer R as a parameter. Okay, write this guy in here. Okay, now, where's the location of the next road going to go at? The current number of roads in collection. We're going to say this collection of roads at bucket, this number of roads in collection is equal to the road that we're adding. This town gets one more road added to it at the current, at the opening location for the next available spot to store a road. And then we need to make sure that we increment the number of roads in the collection. Because the next road we're going to add is going to be at the next bucket. First one we add is at bucket 0. Next one's going to be at bucket 1, bucket 2, bucket 3, so on and so forth. Okay, so now a town knows how to add roads to its collection. Go ahead and save that. So now we'll go back to main. We're going to go back where we're reading in those the parse road, when we're reading in the roads from our thing. We've gotten our towns. Here's town 1, town 2. So when we're done with this loop, we're building our road parts out of a town 1 and a town 2 and a distance. Now, if I go into road parts, you'll see that that guy actually builds a road. Well, I sort of kind of need that road. Well, actually, we can think about this. What's a road right now? A road has a distance and it links 2 towns. Now, I could put into a town, I could say, here is the actual road object that you are associated with it. One of those 2 towns is you. Make sense? But not do some sort of special case. So I could do that. In fact, I probably should do that. The alternative I can say is, you know what? You have a road-like thing that leaves your town and goes to a destination town. All right. Now, in that particular situation, that road does not need to store. If I'm Mequon and I'm putting in Port Washington Road, let's say, I don't need to store that Port Washington Road is between Mequon and Grafton. I don't have to store that because I already know about Mequon. That's me. Okay. Now, does it hurt to, since I already have a road pointer, that guy already exists, this ubiquitous road is just floating out here in space, right? Okay, he's floating out here in space, and this particular road goes between this town pointer and this town pointer. Does it make sense for me to create a whole nother object of kind of a almost just like this guy with just one of the towns cut off, and actually add him to our town and say, oh, well, here's the road that leads to a single other place? Or is it reasonable for us to say, well, if I'm going to take the town out of if I'm going to take a road out of Mequon, we look up the road and we say, okay, I'm going to go to this guy's destination. What's the destination? It's the town that's not me. Right? I got two towns to choose from. Where does this road lead? It leads to the town pointer that isn't the same as me. It's not the end of the world, right? That's a easy enough sell. So we'll store the actual roads. Now, with that in mind, when I'm building a road here, that road does not actually get built. Let's go into this. Actually, I want to go into what's it called? Road collection. Where am I building my road? All right, so here's my new road part. Two towns in a distance. Road parts is up here. Takes in two towns and a distance and sets that guy's and then where am I building my road collection? All right, so this is parse road, so I need to get roads. Here's get roads. Here's my actual road that I'm building. So now that I have a road and I have my two towns, I can let each of these towns know about this road. And we just built that into town. Town knows how to add a road now. Doesn't matter where we do it in here. We'll go ahead and say T1 add road R, T2 add road R. Make sure this guy took in a road pointer. Add road takes in a road pointer inside of town. So I'm saying town 1, go ahead and add a road to yourself. What road? The one we just built that links between yourself and another town with this distance. Similar, I'll do that for T2. I didn't have to create any new objects. I just let these couple of towns know about the pointer to the road that they are involved in. All right, make some sense? All right, so now the towns know about everything. Let's go back up here. I want to clean this guy up. I'll leave the roads alone here for a second. Okay. Make sure this guy still runs fine. Should. Use of this member function is because when I implemented it, I didn't connect it. I didn't do this guy. Where's that written? That's written right here. Add roads is this collection of roads at this bucket. What's my collection of roads? Collection of roads is a road pointer. Okay, that looks fine. This collection of roads at bucket, this number of roads in the collection is equal to the pointer R that goes there. And collection of roads, it should be a road pointer pointer. Is it that? It's not. It's a array of road pointers. That's what that guy is. This guy's going to take in a road pointer pointer. All right, there we go. All right, so that just showed us evidence of all our roads that we wrote last time. Let's go make sure that our towns know about all their roads, because a town has a bunch of roads in it, presumably. So we'll go ahead and, for a town, inside of display, right now a town is showing its town name. Let's go ahead and have it also show roads. We'll do a cout \T, gives you like a tab, just formatting crap. So we'll say roads. Let's say roads leading out. And I'll actually depict in here what we were talking about, how we can use a road object and determine the destination that's not me, that guy. All right. So from the perspective of a town, we know we have this number of roads in our collection. So I'm going to go through all those guys. For int I is equal to 0, I is less than this number of roads in the collection. All right, so I'm going to go through all those roads. And what I want to do is maybe display where does the road lead and how long is the distance. But I want it to not show me. So we'll just kind of show the example there. So we know that the thing that we're going to be dealing with in the number of roads in the collection is a road pointer. All right, so I'm going to go ahead and just give myself a road pointer temp road, and I'll give myself a town pointer temp destination. And we'll go ahead and say temp road is equal to this. It's called collection of roads at bucket I. So that'll give me, just throw that the road that I'm dealing with into a temporary variable, just so I can work with it. Then I'm just going to take a quick guess. I'm going to say temp destination is equal to temp road do roads know how to give us their towns yet? I made them public. So a little bit of a cop out, but we'll take advantage of it. Temp road T1. So a road has a T1 and a T2, and they're both public, which maybe isn't the greatest idea in the world, but that's the way it is, and it helps us in this current situation. So I've taken a guess that T1 is not this town. So I'll just ask a quick question. If T1 is equivalent to what? How do I ask the question? Is the town that is, actually, I'm not saying T1, I'm saying temp destination. How do I say, is temp destination the same thing as me? Remember, I'm implementing this inside of the implementation of a town. So I am inside of the display function in a particular instance of a town. And the question I'm trying to ask is the town contained inside of this variable temp destination, is that the same as me? Because if it is, I want to flip to the other town, right? Because I only want to find out the actual destination that's leading out of me. I don't want to say I have a road going from Mequon to Mequon. So how do I ask the question here? Is the current value inside of temp destination the same value as me? What kind of value is in temp destination? Cat, dog, or memory address? Still crickets. It's town pointer. So a memory address, which leads to a town, right? So the kind of value that's in temp destination is an address. So how do I say, is that address the same as my address? How do I get my address? Do I have a variable that holds my address? Yes or yes? Still crickets. What's the variable that holds if I'm an instance of an object, in this case, I'm an instance of a town. What variable do I have access to that holds my memory address? So this keyword. So I'm saying is temp destination, is that guy equivalent to this? Is the memory address stored inside of temp destination, is it the same as the memory address stored inside of this? If it is, if that's a true statement, I'll just go ahead and set temp destination equal to temp road T2. Just kind of flip it. I guessed wrong. I took a stab at it. Yeah, we're back to the quantum stuff. I took a stab at it. Got the wrong towns. I'll just grab the other one. All right. So what we have right now after this little if statement is I have inside of temp destination where this road leads, and temp road has in it the distance that it is. So temp road knows how to give me distance is actually private, and I don't have a way of getting distance. And we are just lazy bums in our current example. So we're just going to do that because we've already used bad programming practice. So I guess just roll with it. So now we have the ability to get our distance real conveniently. We also have the ability to change our distance. So now from a town, when I go to display this, I can do a cout, and we'll do a couple of tabs. We're going to have this is 4K resolution output, text-based output. And what we're going to do is we're going to say temp destination. Let's see, there's a town. Do we have a get town name? We do. We have a get town name. See, we've used, we did this on purpose. Here's an example of good programming practice where we have our fields as private members, and then we give ourselves getters to get at those fields. Here's an example of bad programming practice where we just make everything public so we don't have to write those extra functions. Don't do this, but do the other one, but we're going to do this. This is what's going to happen. So this is get town name. So this will say the town name of our destination. And then maybe we'll put like some parentheses here. And then we'll say temp road. Distance, right? Distance. Something like that. So when we go through and have our towns display themselves, they will show the roads that come out of those towns, presumably because we've built our towns correctly. Okay. So for our for loop, it's going to go through displaying an individual town. We'll output the town name. Then we'll indent on the next line, roads leading out. Then we'll indent twice and print out the town it leads to and the distance in miles. And if I call display for every one of my towns, I should get a reasonable output of my map. So we'll go back to main here. Here's my town collection. Here's my road collection. What I'm doing right now is I'm showing my output of my road collection. So I'll do my town collection this time. TC dot the towns at bucket I display. This should show us each town and the roads coming out of that town. So Mequon, roads leading out. We have Grafton 10 miles, Cedarburg 8 miles. Grafton, roads leading out, Saukville, Port Washington, Cedarburg, Mequon. So looking pretty decent. So this is kind of our evidence that our towns now know about the roads that lead out of them. All right, questions about all that stuff. So we convinced that we now have a collection of roads that link all the towns, and all the towns know about those roads. All right, so now we have a graph that contains enough meta information for us to maybe use it for something. All right, so now the idea here is that let's assume we're going to have a start location and we want to have an end location. Well, the traveling salesman problem would say, I start and end at the same place, right? I start at my home, the town where I live, and I need to visit every town and ultimately come back home at the end of the day. Okay, so this was our proof of concept that we have our town collection that's filled up with the stuff. All right, so now, well, actually, let me ask you this question. Which of these is our graph? It's a kind of a trick question. What is a graph? If you had to describe a graph to me, what would you say? Go ahead. Okay, give me a little more. I don't think we're necessarily completely wrong yet. Maybe let me ask it a little bit more direct way. What differentiates a graph from a tree? What's different about a graph versus a tree data structure? I'll go back to our notes. We can look at a picture of our graph if you'd like. So that's the graph we've built here. It was like a whole lot of work to build something that little, but we did it with file IO, so we can make it more complex if we want to. So what's the difference between that guy and a tree? Go ahead.
I guess the tree has like a fixed point, kind of like it comes from the top down, like this graph we can build out like any direction.
That, yeah, it really is the directional aspect of it. So a tree, you start at the top, or if you flip it over and think about trees in real life, you start at the bottom, and the tree grows up out into stuff. And specifically with the binary tree, we have 2 children at most, but just the general concept of a tree, an n-ary tree, means that we're moving in one direction, and something low or high on the tree, depending on how you want to think about it, doesn't loop back to something higher up. That doesn't mean necessarily that we can't build our tree with the ability to climb back down the branch you just came from, right? You know, we've thought about when we were talking about at least the high level, the ABL trees, that dealt with the chiropractic adjustments for tree balancing. The idea is he kind of needed to know about the dude above him, so he had to go back to there. And also tree traversals when you needed to visit something and come back. But that's not saying the same thing. If I go back to a picture of a tree, something like this guy doesn't have like an ability to loop back to this guy. Where in a graph, if this was a town, this town could have a road that goes directly to this town, right? Okay, so a graph does not have the implied structure of a tree, which makes it a lot more abstract, right? Because from any perspective, I mean, we're down here, we just outputted and I think saw the correct results. From this guy, we don't really have any crazy stuff here, but if we are thinking about this like Chicago, anybody here live in the Chicago area or very familiar with the Chicago area? Got nothing. Okay. Well, Chicago and a lot of big cities have something called a loop. Okay, so Chicago has the loop called 294. And what that does, I mean, you could stay on 94, which ultimately becomes 43, then that kind of goes through the heart of the city where it's, you have a bunch of stops that you can get off on an exit, get to all these different parts and things like that. Or, for instance, when I'm going to visit my parents who live in downstate Illinois in Champaign, unless I'm stopping at a Portillo's, well, there's one along 294. Unless I have a reason to go into Chicago, I will take the loop to bypass largely the city of Chicago without going to Rockford, way out of my way, right? So in that particular case, if we operate off this map, we could have like a loop, something that goes from Mequon to Belgium, for example. And we could even think about that in our example here. We could have 43 represented on here, Interstate 43, that treat that as a road. And that guy goes from Mequon directly to Belgium. We could just pretend like there aren't stops grafted in Port Washington. And then we could look at this, if we're thinking about this as kind of a tree, that this thing actually does go all the way back up here to something near the top of the tree or the bottom of the tree, however you want to think about it. Make some sense? Okay, so trees differentiate themselves that way. All right, we'll come back on Wednesday and we will start looking at the details of Dijkstra's algorithm and walk through our tree. The punchline of the question I asked a minute ago was, which of these is our graph? The answer is both. They both hold enough data for us to walk a structure, right? In fact, we're going to start with a town and then follow the roads out of that town. Where roads, we can start with a road and find the towns that link to it. All right. I will see everybody on Wednesday.